We're going to be looking at example 7 in our 311 notes. We have an inverted cone, which I've already drawn. It's a water tank. The initial height of it, if it's filled up, is 12 feet, which I have drawn in a side picture here. And the radius is 6 at the top, okay, which I have also filled in our picture. It's drained through a hole in the bottom or the vertex. So I'm showing the picture of the drain. And that rate is 2 feet cubed per second. So that is something that we know. Okay, so that's a volume issue. So the derivative of the volume with respect to time. Okay, you also can tell its volume by looking at the label. And since it's draining, make sure it's a negative 2 feet cubed per second. All right, our job is to find the rate of change of the water depth. So that's a height issue. So we're going to find the derivative of the height with respect to time. And we want to know when that water depth is 3 feet. Okay, that's what we'd like to find. Okay, so we first start with volume. And since this is a cone, we're going to use the volume formula, which is 1/3 pi r squared h. So similar to example 6, we would have a product rule issue here, and we want to remove one of our variables. So we have to be a little bit creative. So we're trying to find the derivative of the height with respect to time. So that one we need. So this is again a situation where we need to remove the radius r. But unfortunately with a cone, the radius isn't constant because as the water drains down, the radius is going to change. So we're going to use similar triangles here to replace the radius in terms of height. A little comparison test. So we can compare the radius as it drains to the top of the cone, which is 6. Same thing here. We can compare the height as it drains to the height of the entire cone, which is 12. If we go ahead and cross multiply, we'll get 12r equal to 6h. And then we're trying to replace the r. So when we divide by 12 over here, we're going to get that the radius is always the height divided by 2. Okay, so I'm going to go ahead and substitute that in my formula. Clean that up a bit. I'm going to get a 4 down here. That's going to go ahead and join the 3. So that'll be 1/12 pi. And then an h squared and an h will make that an h cubed. Okay. Now I'm finally ready to take the derivative with respect to time. So this side rather, is the derivative of the volume with respect to time. Pi over 12 is a constant, so it stays. This derivative is 3h squared times the derivative of the height with respect to time. Okay, last step is to substitute in the values that we have. We're doing this for the height of 3 feet, so we're going to plug that in for h, and we know that the derivative of the volume with respect to time is -2. So I have -2 pi over 12 times 3 squared, derivative of h with respect to time. Cleaning this side up again, up a bit rather, we get -2 equals, so we're going to have 9 times 3, that's going to be a 27. We can do a little reducing by 3, so we're going to get 9 pi over 4 times the derivative of the height with respect to time. Okay, so we're going to multiply both sides by 4 over 9 pi. So coming over here, I got the derivative of the height with respect to time is going to be -2 times 4 over 9 pi. So if we leave that exact, we'll have -8 over 9 pi, which seems a little funny. So let's go ahead and put that in our calculator, and we'll get about -0.28. Now keep in mind our labels. Our height label this time is feet, and our time label is second, and that completes example 7.